Welcome to the first class of stochastic control and communication. The first class of stochastic control and communication. Okay, so basically, stochastic control, in one line, if you want to define what stochastic control is it's basically decision making under uncertainty. So this would be the major part of the course. So the whole course would be that you have a model, you have a system where the system is there is some uncertain in the system. You don't know some information about the system, or something is random in the system, right? Under those conditions, how can you make the best decision possible so that you get your required outcome? That is basically the whole course that we are going to deal with right now. So here are different topics like so the one is stochastic control, right? The other is information theory. uh, then we have communication theory, and then you have some team decision processes or collaborative decision processes. Then you have some theory in economics. All these have the same type of model. So the model is there is a mathematical model, and in that model something is uncertain. Like sometimes it can happen with some probability, sometimes it can happen with some probability. Mm. Usually you don't know the uncertainty. Uh, that part of not knowing the uncertainty and trying to find out what the uncertainty is learning. But if you know something about the uncertainty, say either the statistics of the uncertainty or the probability distribution or the range that it can take. So now, given some information on the uncertainty, what is the best possible decision you can make is what we'll be dealing in this course. We'll be not dealing with more of how do you come up with what the probability distribution of the uncertainty is, which classifies it as a learning problem. We'll say that, okay, I know that the uncertainty is from a certain distribution or has certain statistics. Then what is the best decision I can make? Okay, I hope that is clear. So whenever I say I am a decision making entity, or I am taking decisions under uncertainty, I have two things, right? So one is I have to take a decision. Now this decision is basically a variable from some set of parameters that or alternatives that you can have. So I'll name them A1, A2, AN. You have some set of parameters you can choose out of those things. I've denoted it with A so that it is basically comes as an action. So you take an action at each decision step. You say that, okay, I want to do A1, or I want to do A2, or I want to do A3, right? The next thing that you have is uncertainty. Uncertainty is basically a random variable in the system. It could be some X with some distribution. This distribution, for now, we'll assume that this distribution is known. So you have some uncertainty in the system. This is also a variable, but whose value is not known. Whose value is not known when you're making the decision. When you're making the decision, the value is not known. But you know something about it. You know either the statistics of it, or you know the probability distribution of it, something of that sort, right? Okay. In the absence of uncertainty, this would just fall down as a optimal control problem or control problem, right? With uncertainty comes two things, which uh, which is where most people get confused, and it is not intuitive to see. One is risk, and one is information gathering. So risk is something which we all know intuitively what risk means. Something is riskier than something. You might lose more, you might gain more. So risk is something which everyone knows what it means intuitively. But in this course, we'll try to define mathematically as strict as possible what risk is. Okay. And the second part of the thing is information gathering. So when you have uncertainty, uh, there could be different types of problems that you come up with. So the problem of information gathering is, when do you know about the uncertainty in the system? Okay, so you take one decision and then you know something about the uncertainty in the system. Now you're allowed to take another decision. Then you know something else about the system. Then you're allowed to take another decision. Or you don't know anything. You are asked to take continuous 10, 20 decisions, a sequence of decisions in a short amount of time. You know the statistics of the uncertainty, but at each time after taking a decision, you are not allowed to know what the decision is, what the uncertainty is, right? So, and under these two different types of settings, also, the best that you can do changes. So, the best decision that you can make under these different types of uncertainty also changes, given you have different information gathering policies. So, if you have uncertainty in the system, basically these two things uh, are more evident. Like you see risk and you see information gathering. So, first we'll talk about risk. So I'll start with a small example. Okay, so you have an item, say of worth rupees 100, right? Now, there is a lottery. If the lottery says pay 100 rupees and you enter the lottery, you have an unbiased coin. So unbiased coin gives you head uh, with probability 2 by 3. So unbiased means it's not 50-50. So you get head with probability 2 by 3 and you get tail with probability 1 by 3, right? It's unbiased. Sorry, biased coin. It's not unbiased, it's biased coin. You have a biased coin. Yeah, it's not unbiased, it's biased coin because it's biased more towards heads. You'll get heads with more probability. Right. Now, yeah. So now if you get head, then you win three of these prizes that you have that are worth 100 rupees. So you get 300 rupees. Right. If you get a tail, then you win nothing. You win 0 rupees. Right. So now the decision that you can take is, do I enter the lottery or do I do not enter the lottery? The decision is, do you pay for the lottery or do you not pay for the lottery? Okay, so any guesses? How, okay, could you come up with some logic saying that, okay, how do I calculate, how do I enter the lottery or how do I not enter the lottery?
So yeah, we would like to calculate the expected value.
Exactly. Yes. Yes. Very good. Very good. Exactly. So the first thing that you could do is you could calculate the average outcome you get from joining the lottery. So if you join the lottery, then basically 2/3 of the time you get 300 rupees and 1/3 of the time you get nothing. So this boils down to 200 rupees, right? And then you compare it with how much you're paying for the lottery, cost of your action. Your action here is you are entering the lottery, that is rupees 100. And you see that, yeah, so my average outcome is greater than my cost of action. So your decision is, yeah, you enter the lottery, right? Now, this is the first setting. This is the first setting. Now, suppose I take the same setting and I say, okay, I have the same lottery, but now instead of this 100 rupees, I have 1 crore item which is of value of 1 crore. And the lottery, I pay 1 crore, the same biased coin. I get head with probability 2/3, I get tail with probability 1/3. And if I win, I get 3 into the same item with 1 crore, so I get 3 crores. And if I lose, I get nothing. So, okay, so now, do you think everything in the lottery is the same? The uncertainty is same, everything is same. I've just scaled up the value of the lottery. Do you think, again, your decision would be, yeah, yeah,
So I won't rely on the average thing this time.
yeah, exactly. You won't rely on the average thing. But then, what would you want to rely on? No, it's a good.
So yeah, because now at this time I would be pretty fearful of losing the 1 crore. So I mean, I will
Yes,
change my decisions. Yeah.
you will change your decision. So basically, the yeah, you're absolutely right in this. So what changed from here to here is basically your there is a risk involved in the second lottery to the first lot than the first lottery, right? You are risking more in the second lottery than the first lottery, but this risk does not play a part in your decision making right now because all you're considering is the average outcome, right? You're not considering anything else. So uh okay, so what risk says basically is uh, when you scale the problem really high, your decision need not remain the same. The decision could vary, right? But then you need to come up with a logic saying, okay, if I scale my problem to such, then what should my decision, when should my decision change, and how should my decision change? So here you have seen that in the first example, your decision was based on the average method. You pay the lottery. When it went to 1 crore, you're like, no, I don't want to pay. I don't want to take the risk. Then there should be some threshold, right? If I increase from 100 to 1,000, okay, now do you say that, okay, now the decision is the decision flipping, saying that I would pay for the lottery and then I would not pay for the lottery, or is it 10,000 or is it 25,000? So there needs to be some threshold kind of thing or some mapping that we need to do. And yeah, so that we will go into. So the answer to all this is basically expected utility theorem. You expected utility here or theory, expected utility theory. So what does expected utility theory says? Just looking at average outcomes does not capture our attitude in decision making, right? So we want a way to compare two different lotteries. So when I say here compare two different lotteries, I mean compare two different distributions. Okay, so before going into all this, let us use the examples that we have given above to come up with a base mathematical model that we'll be using in the next couple of classes. So you have D, right? This I'll call as set of decisions. So in the previous example, the set of decisions was either 1 or 0, where 1 could mean that you pay for the lottery. 0 means you don't pay the lottery. So D is your set of decisions, right? Omega is your set of states, or this is your uncertainty in the world, right? In the above problem, you had a biased coin, which could either give heads or tails. You didn't know which it would give. You don't know, you have no control over whether it would be heads or tails, but you know something about it, that some statistics you know about it. Okay. Then you have the set of outcomes. Now, the set of outcomes basically depends on the decision that you have taken and the uh, the uncertainty in the system. So your small d belongs to a set of decisions and your small omega belongs to a set of states. So this would give you an outcome, saying that this outcome would be it is a subset of your real life. So this outcome could be in the previous example. This outcome was you either win. In the first example, it was you either win 300 rupees or you win nothing, right? So it could be one of those two. So the zero could be either 300 or it could be zero, depending on what you have taken. It could always be zero. Suppose your decision is zero. I don't want to enter the lottery. So if your decision is zero, even if your state is head, you get zero. If your outcome, if your uncertainty is tail, you get a zero. If you say no, I want to take a decision, then if it is head, you get 300. If it is tail, you get nothing. Okay, so I hope this mapping is clear, right? So we are taking the above examples and we are mapping it out. Okay, now, okay, this I'll basically call it as system dynamics sometime. System dynamics with uncertainty because you have an uncertainty in omega. Now, system dynamics can take value. So system dynamics would give you an outcome. So you give a decision, it will randomly generate some omega and it will give you an output O. Okay. That system is basically black box. You give an input, that is your decision, you get an output. The next part is now you need to find, okay, which output is better than which. So you have a preference relation. This is a preference relation saying, okay, so if I have O1 comma O2 belongs to the set of O. Okay, this O is set of outcomes. So this O is set of outcomes, and yeah, okay, yeah. So from the set of outcomes, you take O1, O2. Here, O1 could be 300, O2 could be 300. Then what you want is, if I say O1 is less than or equal to O2, this implies O2 is more preferred. I want more outcome, more preferred than O1. You have a relation, you know that, okay, this outcome is more preferred than this outcome. Okay, so this is your, these four are your basic models that you need to remember. You have a set of decisions, you have a set of states that the uncertain random variable can take. You have the system dynamics where you give a decision, it randomly generates an omega from the set of uncertainty and it gives you an outcome. The outcome is random because omega is random, but outcome can take values from a certain set, right? And from those set, you can always have an order relation saying that, okay, I would prefer this outcome than this outcome, but you don't know when which outcome would happen because of the uncertainty in the system. Okay, I hope it's clear till here. Now, let's look at some approaches that we have already seen or some new approaches that we want to see, right? So the first thing is, yeah, average outcome. This is something we saw in the first two things. The one thing that you could do is you could do an average outcome where you take a decision such that you maximize your expected outcome, right? So in the first example, where we had the lottery, this example, yeah, in this example, you can see this is basically what we did. We maximized uh, the average outcome that we saw. So if you participate, then you get 200. If you don't participate, you get 0. So I would want to participate. Why would I don't want to participate? So that is your answer for this. So you maximize the decision that gives you the maximum expected reward. So here, this in the first example, this would occur with probability 2/3, and this would occur with probability 1/3. Similarly, this would occur with probability 2/3. This would occur with probability 1/3. So For the action, for the decision 0, you will get expected value this to be 0. This function would be 0. For the action 1, you would get the expected would be 200. So obviously this is greater than this. So you would say that, okay, I would choose the action where I take this is. I hope this is clear. This is one of the things we could do. The next thing we could do is we could look at the worst case output, right? So what does worst case output mean? I say max D belongs T. You choose the minimum output that you can get, right, over all decisions. So first you're minimizing your uh, output. So first, let's say fix your decision to be 0, right? You fix your decision to be 0, you see that the minimum output that you get is 0. If you fix your action to be 1, you get minimum output to be 0 again. So here, if you look at the worst case, you'll see that it doesn't matter here, uh, whichever action you choose in this case. So it doesn't tell you much if you look at the worst case in this kind of setting. Or you could look at the best case possible. Best case possible, you would be looking at maximizing the decision such that you maximize your output. So these are some of the examples, but then there is, but these approaches are not as complete because again you'll run into the problem of these three does not give you an intuitive answer of what the risk should be. So there are certain better approaches. So that is your expected utility theory, expected utility theory. So, okay, before going into expected utility theory, I just want to mention that you have the omega, the set of states or uncertainty. They have an underlying probability distribution among them. That probability distribution I'll call as P. So what does P give is, if I say P of omega, I'll get the probability of getting omega in the system. Like, so I know it, I know this distribution, right? I know all this thing. Then F d omega will suppose say give you OI, right? Then I'll have a probability distribution over outcomes also. So now this PDOI. So basically what I want to do is I want to see with what probabilities do my outcomes come, right? So suppose I have different outcomes. I want to see with what probabilities my outcomes come. So this is basically probability of set of omega, all the omegas that may give me this OI value. I want to find this probability, right? So PD is the probability distribution on the set of outcomes. What expected utility theorem does is allows me to compare these two distributions. So suppose I have one decision PD1 and PD2, right? Then if I can say something about PD1 and PD2, does that imply that D1 is less than D2 or something like that? So if probability of an outcome in one of my decisions is more than other, then do I prefer that decision or not? If I have some preference relations between the distributions and the decisions itself, then this is what your expected utility theorem does.
So this PDOI, I mean, its interpretation is not that clear. So what does it comprises of?
This PD1 is what you're asking, right?
So PDOI, which says, I mean, whose
Oh,
definition is
oh,
written here? Yeah.
yeah, okay. This definition, you want this definition, PDOI. So PDOI means the probability of getting output as OI if I take D as my decision. Now, similarly, if you have some other decision, if you have some other D, say you have one logic to come to a decision, I have one logic to come to a decision. Suppose your logic is I denote it as PDR. My logic is I say, okay, it's PDA, right? Now, suppose the best outcome is OI, right? I look at both of this. So this is basically probability of getting output OI if I take your logic as a decision. And this PDA-OI is basically probability of getting output OI if I take my logic as a decision.
Yes. Yes.
So now I want to see, is your logic better or is my logic better? Is your decision making better or my decision making? So I want to compare that. So to compare that, I'm comparing basically two probability distributions and saying that, okay, your probability distribution, my probability distribution, I compare and say that, okay, this is, if this is greater than this, then that implies that, yeah, either your decision is better than my decision or my decision is better than your decision. I hope that is clear.
Yes.
So today we'll do one thing. I'll just state the utility. Um, I'll state the utility expected utility theorem. I'll not prove it. It will be too rigorous to prove it. I'll give an example of an expected utility theorem. Okay, I think that would be better. Yeah. So okay, so I'll just state the theorem. Okay, I'll state the theorem, and it is not okay. I'll first state a raw form of the theorem, the basic idea of the theorem. The basic idea of the theorem is there exists a function u. This function, what does it take as input? It takes your outputs as an input and gives you a real number. So it takes outputs also could be real numbers. So it takes some output, gives you real numbers, right? Now, what it says is if D1 is less than or equal to D2, that means that D2 is a better decision than D1. Then this implies the probability distribution of D1 is less than or equal to probability distribution of D2. So all those outcomes which have better value would occur in D2 than in D1. Those probabilities would be higher in D2 than in D1, right? This implies, now comes the interesting part is expected you. Now it's not expectation of just the outcomes, it is the expected utility of the outcome. So you have this UF D omega, D1 omega is less than or equal to expected UF D2 omega, right? So basically, initially what we were doing is we were ignoring this U. We were just calculating the average outcomes. But now you're not calculating the average outcomes, you're calculating the expected utility of the outcomes. Now, this is not always true. Like the theorem says that there'll always exist a U if certain axioms are followed, certain properties, certain assumptions are true. That those assumptions I'm not going into right now, but the high level thing is there'll always exist a function U. This function would basically be concave and increasing. So basically like a log function. It will be a log function. As you go higher and higher, it will keep on increasing, but the rate at which it keeps on increasing decreases, right? That is basically, so this function would be of this form, where it will be concave and increasing function. And now the expected utility, the expected utility of two decisions, if expected utility of decision 1 is less than expected utility of decision 2, it means that D2 is better than D1. That is what it says.
Yes, and what's the reason behind this utility function to be a concave function?
Oh, okay. The reason behind it being a concave function is intuitively, when you prove this theorem, intuitively what comes out is, as you scale the problem, you get less utility from it. So here what happened was, in the first lottery, you see, when your outcomes were just 300 and 0, you had more expected rewards. That you had that feeling that, okay, I'm getting more, so it's better to play. But as I scaled it to 3 crore, my outcomes to 3 crore, you're like, no, I can't take the same decision there. So the concave and increasing part is that the concave part is the rate should decrease because the risk as you keep on scaling your problem increases. I hope that is clear.
Yes, yes.
So that is the main reason for it to be concave. But if we go through the proof, you'll see that the concavity actually plays a part in all the implications of these three. So when I say, yeah, yeah.
Yes, but this D1 is less than or equals to D2 actually. What does it mean? I mean,
Oh yeah,
so
yeah,
how
yeah.
how to quantify this thing that my decision is not better than, I mean, yours?
Yes, yes. So that is a very good point. So here I'm notationally abusing this. This is not actually less than or equal to. I have to mathematically define an order saying that, okay, D1 is strictly less than. Now this strictly less than D2, this weird looking symbol is saying that D2 is better than D1. In what way? I've not quantified it yet. This theorem allows me to quantify in saying that, okay, if your expected utility is less than or equal to this, then your order is preserved here. This is what it does. I'll do one thing in the next class. I'll give you the assumptions of all this. There you will understand what this, the same question basically you asked. What is the preference between, how am I quantifying D1 less than D2? That will
Yes, yes.
be answered. But before that, I just want to do an example so that so that it's clear. Like so for today, I'll just do the example. Yeah, and then tomorrow, yeah, with the next class, I'll not do the proof because it's yeah, I'll figure. I'll say we'll see in the next class. So so today I'll give an example. Okay, yeah. So suppose yeah, you have 1 rupee, right? Now you have two options. There is an investment A, there is an investment B. Now, investment A, if you give 1 rupee, you will get 1.5 rupees with probability 1. Investment B, if you give 1 rupee, you will get either 3 rupees with probability 1 by 2, or you'll get 1 rupee with probability 1 by 2, right? So these are your outcomes. Now, the question is, what fraction of your initial investment amount should you invest in A and B? So basically your decision variable, capital D, is between 0 and 1. Yeah, it's between 0 and 1. Because if you suppose your decision is 0, right? That means you're not investing anything in A, you're investing everything in A. If your decision is 1, you are investing everything in A, nothing in B. If your decision is somewhere in the middle, X into that your decision D, small d, you're investing in A, and 1 minus D, you're investing in B. I hope that is clear. So your outcomes. So suppose you invest everything in B, you will get a maximum reward of 3, right? And the minimum reward you can get if you invest everything in B is 1. So you could be somewhere in between 1 and 3. Yep. So this is your outcomes. And your omegas are basically omega 1 and omega 2. So this is your omega 1, this is your omega 2. The uncertainty lies in the case of B. Here there is no uncertainty. If you put X, you get X into 1.5. Okay. So first before, yeah.
Yeah, what is omega 1 and omega 2 here?
So omega 1 and omega 2 means the outcomes. Like uh, suppose you invest everything in A, right? Then you know that you'll get 1.5. There is no uncertainty there. You know that you're going to get 1.5. But in the system, someone is flipping a coin and saying that, oh, I've gotten heads, so I get threes. I gotten tails, I get one, irrespective of whether you have invested in B or not. So that is an uncertainty in the system.
Yes.
Yeah, I hope that is clear.
Yeah.
Yeah. So now your FDW is basically 1.5D. So okay, so let D belongs to capital D, summation. D belongs to 0 and 1. So suppose 1.5D plus 3 into 1 minus D with probability half. So if you have D amount of fraction you have put in A, so you get 1.5 into D and the rest in B. And suppose then you get heads, then you get 3 into 1 minus D because 1 minus D you have put in B. Uh, or you can also get 1.5 into D plus 1 minus D with probability half. So basically, these are your two outcomes. Yeah.
Yes.
Okay. Yeah. These are your two outcomes. Okay. I understand the question. Maybe writing omega 1, omega 2 here. Yeah. Yeah, it's fine. I understand the question. Maybe writing here is not the correct thing, but you understand what my.
Yes. Now I understood. Yeah.
So, uh, for first thing we can do is first we can calculate average rate of return. We'll not go into utility. We'll do average rate of return. Average rate of return. Average rate of return. Uh, yeah, okay. So mm, average of investment A is 1.5. Average of investment B is 2. So average of B is greater than average of A. So average rate of return would say you put everything in B. The worst case would tell you put everything in A, because the worst case in B is you get 1. You don't want the worst case. You want to uh, maximize your output for all minimum output. So you will say that, okay, put everything in A, right? Mm, yeah. Okay, now we'll come into expected utility. Expected utility is basically what you're doing is maximizing your decision p comma 0. Okay, before going into this maximum expected utility, I'll just write this down more formally. I think it will be more clear. Okay. So In the worst case, basically what you're doing is you're maximizing D belongs to D and minimizing omega belongs to omega, F d omega, right? This is what is your worst case. So you're maximizing D belongs to 0, comma 1. And now you're minimizing over two outcomes. You have two outcomes. One is 1.5 D plus 3 into 1 minus D, or 1.5 plus 1 minus D. So out of these two, which is minimum? So 1.5D, 1.5D is same. 3 into 1 minus D, 1 into 1 minus D. 1 into 1 minus D would always be the minimum. So this would be always minimum. So now you're maximizing D belongs to 0, comma 1 such that 1.5 D plus 1 minus D, which is basically maximizing D belongs to 0, comma 1, 1 plus 0.5 D. This is a linear equation in D, and yeah, maximizing this is basically saying that your optimal D star is 1. If you have anything less than 1, this would be less. So I hope this is clear. So when I say D star is 1, that implies that I'm putting everything in A. Is this clear? Like this calculation, this small calculation?
But then maximum value would be when I put the value of D is equal to 1 here. So
Yeah,
then
yeah,
this max value came out to be 1 point, I mean
yeah.
1.5.
1.5. Yeah. The max value
Uh,
came out to be 1.5, but then what is the decision at which? So what is the decision D star? So basically what this is saying is the D star, the best decision you can take is D star should be 1. When I mean 1, I mean put everything in it.
so what's the rationale behind taking the max of all the mins? I mean, max min.
Oh,
I mean, what's the rationale behind this? Yeah.
the reason behind this is when I asked you a logic, what is the first logic that you get is people get an average rate of return logic. There is also a logic of worst case return. People want to minimize their losses. They don't want the worst case. So you're minimizing over your outcomes and maximizing over decisions. So one of your decision is to invest everything in A. There you know that I'll get 1.5. But when you invest everything in B, you'll get least outcome is 1 you'll get, which is better than the least outcome in A. So you always want to put in A.
Yes.
So
Uh,
yeah, maybe I'm not as clear as I also want to be. It's basically saying that suppose you have two decisions. One decision gives the worst case that you can get in decision one is say 10. You have one more decision. The worst case that gives you is 11. You'll always choose the 11. But maybe the 10 decision, that decision could give you some 100 or 200. This might not give you 100, but then you're not taking the risk. You're saying that I'll just look at the worst case both my decision gives, and I'll take the best worst case possible.
oh, I see. Yes. Yeah.
You don't care how much you win, you just don't want to lose.
Right. Right. Yeah.
Which is a bad thing, because this is one way that people can take decisions, but it's not the best decision that people can take. So now expected utility. So expected utility, basically I'll have max D belongs to 0 to 1. Expected U F D omega. This is what I want to maximize. So the utility theorem states that if my expected utility is greater than all my other decisions, then that decision is more favorable, right? So I want to maximize the decision over which I maximize this. So first what I'll do is I'll write this down as a whole. So max D belongs to 0 and 1 such that I have half U 1.5D plus 3 into 1 minus D plus half U into 1.5D plus 1 minus D. Okay, so Just small play of words here. This half and this half, it doesn't matter if I'm maximizing with half. I can just take half out common and maximizing this would be sufficient, right? Now, the utility theorem guarantees the existence of U, but it doesn't say what U is. So that is also actually a nice question and saying that, okay, how do I come up with U? So for this example, today what we'll do is I'll give you an U. I'll give you a U. So U of X is alpha X minus X squared. Okay, where alpha belongs to R and alpha, okay, alpha is greater than 6. So alpha is greater than 6. And why did I choose alpha to be greater than 6 is because I want that increasing in it should be an increasing function. So this should be a concave and increasing function. So increasing function would mean that I take a derivative with respect to x. I get alpha minus 2x. Now this should be greater than or equal to 0. The derivative should be increasing. It should be an increasing function. So this implies that alpha is greater than or equal to 2x. But I know that my outcomes can be at most 1 or 3. Right? So alpha should be greater than or equal to 6. If it is equal to, it will not be an increasing function, it will be constant function. So I'll eliminate this equality here. So, okay. So my utility function is alpha x minus x square, where alpha is greater than 6. Okay. I'll just write down f d omega again. Uh, but now instead of writing the whole thing with different d's, I'll write them in a single expression. 3 with probability half and 1 plus 0.5 d with probability half. So now u of f of d omega. This also you need to write. This would be alpha of 3 minus 1.5 d minus 3 minus 1.5 d whole square. These are just calculations. If you feel bored, I might skip the calculation and write down the whole thing at once. But I think calculation once will give you some idea on what is happening. So minus 1.5 d minus 2.25 d square minus 9d probability half 0.5 this alpha minus 0.25 d square minus d with probability half. Minus 2.5 d square minus 9d. And the second one is minus 0.25 d square plus 0.5 d alpha minus d. Yeah. So now I basically need to add these two because half into half I take it out common. So basically I add these two and I get maximize d belongs to 0 to 1 minus 2.5 d square plus from these two d into I take the d common out here 8 minus alpha. So I just want to maximize this function. I take this derivative of this function. Let me call this function g of d. I take the derivative with respect to d. I get minus 5d plus 8 minus alpha. I equate it to 0. and I get d is equal to 8 minus alpha by 5. But then this is true only when alpha is less than or equal to 8, less than or equal to 6. If alpha is greater than or equal to 8, then d equal to 0. Because, okay, so yeah. So you have this 8 minus alpha, right? You have this 8 minus alpha here. Now suppose in the cost function, if alpha is greater than 8, then you'll get a negative term here. And then you'll get a negative term. So you want to maximize this whole term. You would just choose d to be 0. You don't. I hope that is clear.
So how did you reach? So how did you reach to this expression? Say
So,
minus 2.5 d square plus
so
d and then 8 minus alpha.
yeah, this expression. So you understood this expression, right?
Yes, yes.
So from here, I can write this as 1.5d minus 3d. So that would give you minus 1.5d. So minus 1.5d plus 3. So plus 3 minus 1.5d. This I've basically written as 3 minus 1.5d. And this I can write it as uh, 1 plus 0.5d, right?
Okay. Mhm.
Yeah, so I have written it 1 plus 0.5d here. Now, I know my utility function. My utility function is, this is one of my outcomes. So I want to find the utility for this. I want to find the utility for this. The utility for this would be u of 3 minus 1.5d. That is alpha into 3 minus 1.5d minus 3 minus 1.5d whole square. Similarly, the utility for this is alpha into 1 plus 0.5d minus 1 plus 0.5d square. And yeah, that is basically these two terms I've written here. So this term I have written here, and this term I've written here. Yeah.
Yes.
And then basically this one step is basically calculation. So you just expand this square and you do this. There might be some mistake here. I'm not sure. You can check it out once later. But yeah, this is just basically calculation of this. The next thing is now I want to find the expectation of this function. Since this is a random variable, right? U of f of d of omega. The randomness is omega. So you have this probability. So the expectation would be half into this plus half into this.
Oh, I see. Yes. Now I understood. Yeah.
So what I've done is I've taken out half common because I'm maximizing over it, right? So maximizing over half, like maximizing half x plus half y is the same as maximizing x plus y.
Yes, yes, yes.
So I've taken both the halves out common and I've just added these two and put them here.
Mhm, mhm.
And from this, you can see that if alpha is greater than 8, then um, yeah, then this term is also negative, this term is also negative. The best decision you can take is d equal to 0. If alpha is less than 8 but greater than 6, then you have a play around with d. So basically your optimal decision would be 8 minus alpha by 5 if 6 is less than or equal to alpha, less than or equal to 8, 0 if alpha is greater than 8. This would be your optimal decision. And okay, so yeah.
Yes, but we could have selected say some other function instead of
Yeah,
taking say this. Yeah.
yes, you're absolutely right. We could have selected some other function. Now, basically, what is happening here is you have this. Uh, so if I okay, I'll put this in the color. Suppose I don't have this, right? I don't have this term minus x square. It's just alpha x. Then basically, you're basically doing expectation first. The first moment you're doing the average. That is just the average. If I don't have minus x square. Now with the minus x square, I am introducing more information in the system. Like I'm taking out more information. I'm doing a second moment now. Now you can keep on adding moments to your function. Like you could have basically your ux could be e power minus e power 1 minus e power minus x or something like that, which is concave and increasing. And which will have all the moments. Now 1 minus e power minus x, you can do the power series expansion and say that, okay, now I have first moment x by 2, I have x square, you have x square by 2, x cube by 3, x power, you have all those moments. So basically what you're doing is you could, the next best utility function you could do is you could add plus some term of x cube minus some term of x power 4 plus some term of x power 5. The more moments you add, the more better notion of risk you get. Uh,
Yes. Yeah, yeah.
yeah. So that is what you see. So here, when your alpha is, so you now have just two moments, and when your alpha is greater than 8, let me just get the charge. So when your alpha is greater than 8, what it says is um, you're getting more utility in B than from A. So when your alpha is greater than 8, what will happen is the outcome that you get from here 1.5 times is actually less than this 3 into 1 by 2 plus 1 into 1 by 2. So it's saying that put everything in B than putting it in A. If you're between 6 and 8, it says that, yeah, it's not worth the risk. Put some fraction in A, some fraction in B. If your alpha is greater than 8, it's saying that, yeah, put everything in B. So yeah, this is an example. So okay, so today I want to stop the class here. I'll stop the recording. Uh, just
So, yeah, which book would you be following for this?